Awesome. All right, so today's lecture is going to be about atoms and elements. It's going to cover a wide variety of different topics, and we're going to go through the periodic table, which is my background for my Zoom chat, right? So we're going to cover the different parts of the periodic table, the different laws that govern our elements and how they interact with each other. So, and there's a bunch of laws in the beginning. Then we're going to go through the different types of elements and then the different types of, more detailed different types of elements, then their interactions with each other and how the periodic table is organized to show this very nicely. So first, here we go. So Crash Chem. So I mentioned it last class, but definitely follow Crash Chem. I think I have one more follower from you guys. I'm not going to say like follow me and you get extra credit. That's kind of weird. But at least you can look up, if you don't want to follow it, you can look up hashtag Crash Chem NJIT, and you can see these short snippet videos that I made going over really important concepts. And one of those, I think a couple of the videos go over concepts that we're going to learn today, such as the periodic table organization and basic, I think I have a bunch of them on atomic composition and things like that. So it'll be very helpful when you're studying. But if it's really easy, too simple for you, that's fine. You don't have to do anything. But yeah, so let's continue. Law of conservation of mass. So it's one of the easiest laws, and you've probably heard it all through high school in any science class, is that mass cannot be, or matter cannot be created or destroyed, right? So it's this idea that the universe has a set amount of matter, and you can't add or remove any. And that's kind of a law, and that's kind of a law. It's a law, but it's kind of been disputed lately, because ever since the discovery of dark matter, there's been scientific evidence that you can create matter. There's very small amounts of matter, like we can't even detect it almost, like maybe 15 zeros and a 1 milligrams or something that we can't even detect. And there's been experiments to show that, oh, that was created out of basically nothing, or created out of just pure energy. So it's a weird law, but in general, in all of our tangible chemistry that is not in the quantum realm, we say that matter and mass cannot be created or destroyed. So, and here's an example of that. You react some solid sodium with some chlorine gas, and you get the exact amount added together of sodium chloride, assuming that it all reacts equally and there's no excess. So this is the amount that would react completely, and you get 7.7 plus 11.9 equals 19.6. So the total mass in any chemical reaction of the reactants has to equal the mass of the products if it's in a perfect world. So in experimental chemistry, let's say you're in your lab, you're never going to get that. This means 100% yield. So theoretically, they call it a theoretical yield, where on paper you do the stoichiometry and you do the math, which we're going to learn in this class, of how much of a reactant should react with another reactant out of how much you have to create a certain product. That is only a theoretical yield. So if you actually reacted 7.7 with 11.9 in a lab, you might get 10, 15 maybe grams of NaCl. It doesn't mean that matter was destroyed or matter was lost in like the universe. It just means that your reaction didn't go through completely because, let's say, because of human error, or your container, your chlorine gas, if you open this chlorine gas, most of it's going to just go out into the atmosphere. Anyway, you wouldn't be able to fully react it with the Na. Even if you drop the Na in, there might be some experimental error going on. So experimental error makes the theoretical yields really never achievable, because we're human, and also our instruments are created by humans. No matter how precise they may be, there is always some error, like we were talking about last class. Okay, so the next law is the law of definite proportions. This is very basic, so it's kind of like, oh, no, duh, of course that's true, right? And it says that all samples of a given compound are that given compound in a specific ratio, or a specific proportion of their elements. So, for example, you have CO2. It's CO2. If it's in a canister, if you breathe it out, if it's dry ice, like remember we talked about If CO2 is a really low temperature, I think it's negative 122 Celsius, I think, and it's solid, it's still CO2. It's not like some of the molecules are CO and some of them are CO3 and some of them are CO2. They are all CO2. That's what makes that element its characteristic properties, that it's has that proportion of carbon to oxygen. If you have, oh, some of them are just CO. What is CO? CO is carbon monoxide. That's going to kill you. So you definitely need this law to live. If it was kind of like a loose thing where, oh, some oxygens could just come off and randomly go back on the carbon, you're going to really encounter some problems. So the law of definite proportions, it's no matter where they're from, if it's the same compound, it has the exact same definite ratio of one element A to element B. And here's an example with water. And also, it's not just a ratio of the elements, it also means a ratio of the masses. So something we're going to learn in this class is molar masses. And maybe if those of you who took chemistry in high school have seen this before, but those of you who have not, it's okay. And the periodic table will help you a lot with this. So with water, which is H2O, get my pen out. Water, so H2O, you're going to have H, the molar mass of H, meaning 1 mole of it, we'll talk about that later, is 1 gram about. So if you have 2 of them, it's going to be 2 grams, just like it's right here. So if you have, hold on, I'm going to move my drawing tool. All right, so if you have 2 grams and you have 1 oxygen, the molar mass of oxygen is 16 grams. So if you just say there's a ratio of 16/2, you're saying that that is a definitive ratio. So it's an 8-to-1 ratio of grams of oxygen to grams of hydrogen, or the ratio is just 8. And this is going to be true for all water. So that's, yeah, it's constant composition. Okay, so basically the same thing. There's ratios with every type of compound. If you do NaCl, there's ratios, there's more ratios. So they're the same no matter what the source is. You got the point. Okay, then there's a law of multiple proportions. Now, personally, I hate this law because it's really tough to teach, and also it's not really that important anymore. So here's what I mean. Well, it's still true, but it's not really that important. So here's my best explanation. Now, when 2 elements, let's say we can use A and B, but we're gonna use like C and O, right? When 2 elements, C and O, form oh, Chris raised hand. Oh, another thing is you could do that too. You can raise your hand.
Yeah, I didn't want to just interrupt you.
Oh, definitely, yeah. Click the raise your hand button. That's actually a lot better. And I could see it in the top right. So, okay, what's up, Chris?
Regarding the law of definite proportions,
yes.
I was looking at it and how you determine the one that goes in the top of the fraction.
Oh, it doesn't matter. So this is just saying that there is a ratio and that ratio is constant. It doesn't mean that ratio is a whole number. It doesn't mean that ratio is larger than 1. It just means that there is a ratio. And if you took water from different sources and you took the grams of oxygen over the grams of hydrogen, it would be that constant ratio of 8. If you took the grams of hydrogen over the grams of oxygen, it would be 1/8.
So what if it was a compound consisting of 3 elements, though?
Right. So the mass. So let's say that's a good question. So let's do, I don't know, Na2CO3. That is sodium carbonate. So if you have sodium carbonate, you can say that the mass of Na over the mass of carbon is, for every one of these molecules, is the same. The mass of Na to the mass of oxygen for every one of these molecules is the same. And then you can say the mass of carbon to the mass of oxygen ratio is the same. I'm saying they're not going to be equal to each other. They're going to be equal in every source of Na2CO3.
Oh, yeah, that makes sense. Thank you.
Okay, cool. Yeah, it's not too complicated. It's kind of like, just like, oh yeah, there's water from one place is the same as water from the other place. Duh, kind of thing. That's what it's saying. Okay, good question. Yeah, so another thing to keep in mind is these laws were created when they were first figuring out chemistry. So these were ground rules they had to establish. Now that even someone who doesn't take this class basically can figure these out and be like, oh, that's a no-brainer. But back in 1700, they weren't no-brainers because we were just figuring out about this new world of atoms and molecules that we couldn't even see. So we had to establish these ground rules. Okay, so law of multiple proportions. So you're going to have two elements that form different compounds. CO is a great example. You have CO and you have CO2. So carbon monoxide and carbon dioxide. Now what it's saying is that when the masses of element B, or it doesn't matter which element, honestly, the masses of element B, let's just be consistent with here. Let's say this is A and this is B. When the masses of element B, so oxygen, combine with 1 gram of the element A, so how much per gram, how much of oxygen per gram of carbon is reacting, they can be expressed in whole number ratios to each other. So here's what I mean. I'll do this math right now. So oxygen, and if you get lost in the molar masses, don't worry, we'll cover that later. So oxygen in any case is 16 grams per mole. If you take it, oh, what did I just do? Click the button. Okay, so 16, if you take carbon, it's 12. So the mass of oxygen per 1 gram of carbon in CO is 16 over 12, and I'm too tired to do math. So let's get my calculator out. 16 divided by 12. And that's 1.33. So 1.33. Now, if we do the same ratio for CO2, element B, which in this case there is 2 oxygens, so we'll have 32 grams over carbon, which is 12. And this is going to equal double of that, right? You have 16 over 12, 32 over 12. So it'd be 2.67. If you take, so that's saying that we basically just did law of definite proportions for each of these compounds. For CO, it's a 16 to 12, oxygen to carbon. For CO2, it's a 32 to 12, oxygen to carbon. So now, if you say, all right, compound 1 and compound 2, wait, Chris, do you have your hand up again, or is that just?
No, I don't know how to remove it.
Oh, I can click it, lower hand. All right, cool.
All right, thank you.
All right, so now if you have another question, I can see it. All right, so if you have compound 1 and compound 2 of these ratios, if you divide these ratios together or by each other, you get a whole number. And that works for every compound that has the same elements. Oh, hi, Adnan. It's okay, I got your attendance. Okay, cool. So, so if you take 2.67 divided by 1.33, this equals exactly 2, or about 2, whatever, because it would be exactly 2. So does that make sense? Is there any questions on that? We'll do another example though. And it's saying that why this is important is because you establish the ground rules between different compounds with the same elements, that there are very similar ratios that they occur in. So Gio says it makes sense. Awesome. Good. So let's continue. And oh, I already did this example. Cool. And here's another example that's more complicated with nitrogen and oxygen. So nitrogen and oxygen actually form 3 compounds, technically a lot more, but the main 3 that are chemically stable, you have, did I see my cat in the back there? She's meowing. Okay, so you have nitrous oxide, nitric oxide, and nitrogen dioxide. So I will write the formulas for them. Your nitrous oxide is NO2, nitric oxide is NO, nitrogen dioxide is NO2. So, okay. So if you do the same exact math and you do nitrogen gas grams, which is 14 is the molar mass, divided by the oxygen, it would 14 divided by 32, you would get, wait, mass of nitrogen per oxygen. Wait, did I mess this up? Oh, I messed that up. I messed that up. I wrote NO2 twice. It should be N2O. N2O. I should have the chat window up. Let me see. Yes, I messed up. Thank you, Brandon. I caught it. Okay, so if that's the case, you're going to have 14, which is the grams of nitrogen, times 2, which is 28, divided by 16 of oxygen, and you're going to get this ratio of mass of nitrogen per 1 gram of oxygen. And then you do the same exact thing for the other 3, and you see they are whole number ratios apart from one another. So, and you can see how that works out. So yeah, cool. That's the way that's the law of multiple proportions. Okay, moving on to Dalton's atomic theory. Now, in the same time period, around the 1700s, 1800s, I don't even know whenever. I don't know my chemical history too well, but it doesn't matter. We're on the cutting edge. So, the Dalton's atomic theory, basically, he came around. He was like, "Oh, there's got to be." It's very basic. He came around and said, "There got to be elements, something that makes up my desk, something that makes up my computer. It can't just be computer. It's got to be a lot smaller than that." So he proposed these 4 postulates that some of them may be true, some of them were not. And the basic ones were, so postulate number 1, each element is composed of tiny indestructible particles called atoms. That is true. So he means by each element, if you take something in the elemental form, it's composed of its atoms. Just like we talked about last class, if you have elemental gold or elemental aluminum foil, it's going to be composed of billions and billions of gold or aluminum atoms, respectively. Then the second one, all atoms of a given element have the same mass and other properties that are different than other atoms of other elements. Okay, this basically means that if you take hydrogen from my room and hydrogen from all of your rooms, it is the same exact thing. It's the same mass and other properties. Now, today we're going to learn about isotopes. And that kind of like borderline makes a gray area with this rule, because with isotopes, you could have the same element with different masses. But if you're taking the same isotope, let's say hydrogen 1, right? And most of it's hydrogen 1, 99.98% of it's hydrogen with a mass of 1. If you take that from my room and your room, it's going to be the same exact element isotope. So 2 is basically true. He had the right idea. Then number 3, atoms combine in simple whole number ratios to form molecules of compounds. Molecules or compounds, that should be. 4. There we go. So this is true because you can't have 0.2 of an element of a compound, or sorry, of an atom. You can't have 0.5 of an atom. So whole number ratios, just like we went over. 4, in a chemical reactions, atoms of one element cannot change into atoms of another element. This is generally true, and it basically means in any chemical reaction, the atoms simply rearrange and attach differently. But when we discovered nuclear reactions, which are chemical reactions, that is not true, because you can have a nucleus explode and the atoms will actually change. Some protons might come out, neutrons will come out, and you'll have 1 or 2 or maybe 2 atoms become one atom, of a different element. But these things can change. So the elements can change into other elements. So he had the right idea. For somebody without any really solid experimental techniques, he did a really good job. Okay, so now we're going to talk about the mole. Or is there any questions up to now? No? Okay. So now we're going to talk about atomic mass and the mole. All right, so atomic mass is not too hard. And it basically is written on the periodic table. And the mole, let's try to understand this. So it's basically, let's just keep going, whatever. So in the periodic table, we have symbols like this. This is your periodic table atomic symbol. And the top number represents your atomic number. The atomic number is a whole number and is the number of protons in your element. So keep that in each atom of your element. So very important thing, atomic number, number of protons, whole number. And the periodic table goes in order. Is there a periodic table up here? What I could do. I'll have one up. pull one up. Now. So basically, once I get it up, come on. There we go. Can you see the periodic table on my screen or no?
No.
No? Okay. That's because my sharing is
No.
different. Okay. Now you can.
Yeah.
Yeah.
Okay, cool. So you see the periodic table, it is in order. There's many different orders, but the main order it's in is in order of atomic number. Hydrogen is number 1, helium is number 2, lithium is number 3, and you kind of read it like a book until you get to the end. So what this is saying is that the atomic number is the number of protons, and the number of protons increases as you go along the periodic table, reading it like a book from left to right, up to down. Then you have the bottom number. The bottom number is usually a decimal, and it marks the average atomic mass. So atomic mass is in units of technically AMU, which is atomic mass unit. Then you can, through conversions, you can convert that, it's the same number as our molar mass. So the atomic mass unit is a different unit, and it's a very small unit. So what you can say is 1 atom of chlorine equals 35.45 on average, AMU. What you can say also is 1 mole of it, a mole is a gigantic number, which we'll talk about in a minute. A mole of it has a mass of 35.45 grams per mole. So we're using that same number, and they made a conversion. The reason why they made AMU is because they wanted to make it easier for us. We want to use the same number on the periodic table for the atomic mass of each atom and the molar mass of each mole of atoms. Because moles of atoms are what we are talking about when we do experimental chemistry. Because we're not going to be dealing with singular atoms where there's just too many and they're too small. So the molar mass is the same number, for our intents and purposes, is the same number as the atomic mass of a specific atom of that element. But obviously the molar mass is a lot larger and it's on a grander scale, and it's per 1 mole. So per a large amount of these atoms. So the reason why I say average atomic mass is because of this phenomenon of isotopes, which we'll talk about in the next slide. An isotope is basically an atom of the same element. So let's say chlorine. There are 2 isotopes of chlorine. One of them has a mass of 35. The other one has a mass of 37. So an isotope is basically the same element, and there's different types of atoms of that element. They have different number of neutrons. The protons and the electrons are the same, but they have different number of neutrons. So chlorine happens to have 2 natural isotopes. One of them is 35 and one of them is 37. Now, if you take the random sample of chlorine in the environment, you will have an abundance of one over the other. Sometimes it might be equal, sometimes it might be heavily weighted towards one, but there will be different natural abundances of each isotope of an element. So chlorine 35 happens to have about 76% abundance in a natural sample of chlorine. Chlorine 37 happens to have 24% abundance in a natural sample of chlorine. If you take the average atomic mass, or the weighted average of these abundances, you get 35.45 about. So if you do that math here, kind of like if you were to calculate your test grade or your grade for the class, and you know that exams count for 20%, homeworks count for 10%, they're going to be weighted differently. So you would take your test grade of 100 and multiply it by 0.2, and then you would take your homework grade, multiply it by 0.1, and then etc., and add those numbers together. That is exactly what we're doing with this weighted average of the isotope mass to figure out the average atomic mass. So if you have 35 for one isotope, 35 AMU, and you have 76% abundance for that isotope. It would be times 0.75 whatever, plus the other isotope of mass 37 times 24%. That equals 35.5 around, so 35.45 if you want to be exact, of an AMU. And if you take a mole of that, a large amount of these atoms, it would be 35.45 grams in that mole. So does that all make sense? And if not, you can ask questions now. Good. Okay. Okay. So here's isotopes. So in an element, we're going to talk about composition in a couple of questions, in a couple of slides. But you basically have the protons, the neutrons, and the electrons. Now, the protons are characteristic of each element. They do not change. If you change the number of protons, it is a different element because of our periodic table, which we talked about, right? That each element has its own atomic number, and that atomic number is the number of protons. If you change that, you are definitely immediately changing the element, even if you keep everything else the same. You can have zirconium and niobium, and they can have the same number of neutrons and electrons. The only thing that makes them different is the number of protons. One of them has 40, one of them has 41. The other numbers could be the same. So if we know that, we can say that, all right, chlorine, there's 2 isotopes. And for other elements, it might be 5, 10 isotopes. It might be a lot. That every chlorine has 17 protons because it's atomic number 17 right over here. Then the number of electrons, that can change, but right now we'll just say it's 17 each because it's neutral. And the number of neutrons changes in each of the isotopes. So you have a lighter isotope, which has 18 neutrons, and a heavier isotope, which has 20 neutrons. And then the masses will therefore be different because protons and neutrons correspond to the mass, which we'll talk about in the next 2 slides. So, not really a trick question anymore, but this was a trick question here. Now it's a trick question. So carbon has 3 isotopes, 12, 13, and 14. The average atomic mass is 12.011. What percentage of carbon atoms weighs exactly 12.011? And you saw the answer, it's none. And the reason why is because 12.011 is an average atomic mass, like we just talked about. That means if you take the weighted averages of abundances, if you take the weighted average and abundances of the different carbon isotopes, they will have a weighted average of around 12.011. So carbon 12 is around 98%. Carbon 13 is around 1% or 1 point something, 98 point something. And then carbon 14 is around 0.4%. So these are the natural abundances. And you can see how you take the weighted average of these, it will be really close to 12. So 12.011. And this is a way that looking at the average atomic mass, you can almost tell which, or you can probably tell from most of them, which isotope has the most abundance if you knew the different isotopes. So this one, 12, 13, 14. Oh, the average atomic mass is closer to 12. Therefore, most of it must be 12. If we looked at chlorine example from before, 35.45. We know there's a 35 and a 37. Good question, what happened to 36? It's just not stable with 36 for some reason. These, well, energetically, not for some reason. Energetically is the reason. The nuclei have a specific ratio of stability when it comes to number of protons and neutrons. And 35 and 37 are that stable point for chlorine. And you can tell if it's a 35 and a 37, it's 35.45. That's closer. If it was 50-50, it would be 36. It's closer to 35, therefore most of it must be chlorine 35, and that is true. It's 76%. Okay, so moving on. Oh, let's get the gifts going. There we go, Jimmy Neutron. So, proton. This is the composition of the atom. Very important slide. I expect you to know, well, you should know by the end of the course, but by now you should know by the end of this class, the charges, location, and masses, and in AMU, approximate masses of the proton, neutron, and electron. So the proton is positively charged, located in the nucleus, and has a mass of 1 atomic mass unit on about. A neutron is neutrally charged, and it's located in the nucleus, has a mass of 1 AMU as well. So for our intents and purposes, we say that the protons and neutrons have the same mass. This, however, is not true. Protons have a slightly less mass than neutrons. Neutrons weigh a little bit more, and electrons are negatively charged, -1. They're located, they surround the nucleus, and they go around, they orbit the nucleus, like you see here. And they're very small. They're located in different energy levels. And we can say their mass is about 0 for our purposes. And I'll explain that. It doesn't have a mass of 0. I'll tell you the mass right now. It's 0.00055. I had too many zeros. Let's see. I think that's right. 0.055 times. Yep. So it's that. It's 3 zeros and a 55. Okay. So the reason why to us, this is negligible is because this is a little bit less than 1/1800th of 1 AMU. So if you multiply that number by 1800, you get about 1. You get 0.99. The periodic table, as you saw before, the periodic table has up to 118. And we're not even going to talk about anything really past 100 because it's kind of weird, but we might deal with elements to 118. Who knows? If you have 118 electrons, that is nowhere near a 1 AMU. So it's going to be 0.1 AMU, not even 0.1. So we're going to just take it negligible. We make it negligible. So it doesn't matter. Fun fact is that, I hope that makes sense. Fun fact is that the neutron is actually heavier than the proton and the electron put together. So nobody really thinks about that. But the weight of a neutron is about, let's see, 1.008 or 1.0078 something AMU. It's around that. The weight of a proton is 1.00, actually this one's 1.78. This one's 8 something. That's sloppy. So the proton has a mass of 1.0078 AMU. The neutron is 1.008 something. Now, since the electron is only 0.00055, you take the proton plus the neutron plus the electron, it's still less than the proton. That's pretty cool how that works. This is like 8.5, or I don't even know what it's a bit more. So it's a bit more than the mass of a proton and an electron put together. So that's pretty cool. But we still assume that the neutron and proton are around the same size. Oh, so there's a question. So anybody want to answer a question? I feel like I've been talking too long. So what do you think the purpose of the neutrons are? So they're neutrally charged. They don't really do anything. They have mass. That's good. And they're just in the nucleus with the proton. So what do you think their job is? Anybody can answer. Anybody? Did I put you all to sleep already?
I'm sorry, what was the question?
Oh, so the question was, what is the purpose of the neutrons, you think? So they're neutrally charged, they don't really interact with anything. What do you think the purpose is?
They keep the electrons from going completely to the protons, and because they're attracting each other. So then, I don't know. I feel like the neutrons have something to do with that.
Okay, so you're on the right track when it comes to charge, right? But not exactly. So it's nothing to do with the electron. It's very little to do with the electrons and more to do with the protons.
Do they keep the protons spaced out?
Exactly. Good. Wait, who said that?
Me, Tyler.
Oh, Tyler. Good. Awesome. So that is exactly right. Protons are positively charged, right? So think about magnets. If you put two positive ends of a magnet together, what are they going to do? Repel each other. And if you don't have any buffer system, that's what the neutrons act as. They act as a buffer system. If you don't have any buffer system and you have two or more protons just bouncing into each other, eventually what will happen is they will bounce off each other, and when they do, they will gain speed more than an elastic collision. So an elastic collision from physics, if you collide two objects, they bounce back at the same momentum, with the same momentum as they hit in with. But this will have a repulsive behavior, meaning they will bounce back with more kinetic energy than they started out with. So they'll keep getting faster. Then they bounce against each other again, faster, faster, faster. Eventually, the force of the protons hitting against the nuclear force holding in the nucleus is going to become outweighed, and the protons are actually going to break through if there isn't enough neutrons, or if there's too many neutrons. If there isn't that happy zone of neutrons, you're going to get protons colliding together, and there's going to be a lot of energy in the nucleus, and the nucleus will actually explode. Does anybody know what this is called? I'll give you a hint. I mentioned it already in class. When the nucleus explodes into this, because of this. Anybody know? Good job, Sarah. Nuclear reaction, that's exactly right. So when the nucleus disintegrates or explodes, and good, fission, awesome. So yeah, nuclear fission is what occurs. And this is why it happens, is because the unstable radioactive isotope does not have its quote unquote happy zone of neutrons to proton ratio. So that's a cool way to think about it. Okay, so any other questions before we move on? No?
For the carbon example that we had earlier, it was like for the isotopes, carbon
Yes.
can only have 35 and 37.
Oh, you mean fluorine?
Carbon can only have 35 and 37 neutrons. Is that because of the spacing? Like
So
36 wouldn't work.
first, so we're talking about chlorine for that one.
Yeah, sorry, chlorine.
Yeah, it's okay. And that's not the neutron. So 35 and 37 is the mass. And the mass is going to be, I didn't specifically say it, but I'll write it down. So the mass number for each of the elements is going to be, or each of the atoms is going to be protons plus neutrons equals mass.
Okay.
So each chlorine has 17 protons. And then there's 35 and 37. So you're going to have 18 neutrons and 20. And Tyler, you're exactly right. That is going to be because for some reason, energetically, the chlorine nucleus likes to have either 18 to buffer out the 17 protons, or it could even handle 20. If you have, you can totally make chlorine with 17 and 19, but for some reason, it's not very stable, and it would disintegrate, and it would cause a nuclear fission in maybe a couple of seconds. So it's not even worth putting it on the chart for a stable isotope because it's unstable. So that's a good question. Yeah. So the isotopes that we talk about in general chemistry, generally, when we don't say they're radioactive, they are stable isotopes, and they can be in a bucket for months and they'll be fine. But if you have radioactive ones, they might only last for a few minutes or even a few seconds. So that's why we don't even consider this one. Good question. Okay, moving on. So how do we discover all this stuff, right? They're such a small amount and such a small, the atoms are so small that we can't detect any of this with looking at it or basic techniques. So that was changed when we came out with the mass spectrometer. It's actually not a spectrometry method because there's no spectra involved. There's no like light, but anyway, they call it mass spectroscopy, the spectrometry. I took a course on this in graduate school, and it's pretty tough technique. So basically how it works is, well, let's look at pictures, they're easier. So you have a sample, and this sample has to be a gas sample of, so you can make anything a gas. So you have chlorine, a brick of chlorine, a brick of sodium. You either increase the temperature, increase the pressure, or sorry, decrease the pressure enough, you make it a gas. Once you have it in a gaseous form, you ionize it. So if you have sodium as a crystal or whatever, put it in a gas, sodium gas, you have to ionize it. There are many different ways of ionizing a beam. A beam of particles. We're not going to talk about this now, but you could throw electrons at it, and that kicks off electrons. You can throw alpha particles at it, and it kicks off electrons. You can take away electrons. You can do different things. But anyway, you'll give it a charge, either plus or minus. Once that charge is achieved, the sample will go through a magnetic plate. These magnetic plates will divert the now charged gas to the detector. And the way it works, it separates them on the detector by their masses. And does this this magnet is an electromagnet, and it has a magnetic field in the middle, and it's very sensitive. So you can detect the difference of masses of one proton versus another, even one electron. So the heaviest particles, so if you have Na, let's say you have, I don't know, hydrogen, right? You have hydrogen gas. You shoot both of these through the detector, through the mass spectrometer, you're going to have the sodium, since it's moving slowly, it's going to be moving more slowly, but assuming they're moving the same speeds, and you have a magnetic field to divert them. What will happen is, since it's so big, it won't divert all the way. It won't divert as much as a lighter element, as a lighter isotope. So you'll have sodium over here towards this part of the detector. Meanwhile, the very light hydrogen will deflect more. Deflection will deflect more because it's lighter and it can move easier, and it responds more, it responds better to the charge in the magnetic field. So that's where the lightest particles will be over here, like hydrogen and things like that. So that's generally how we came up with, not we as scientists, I can't even put myself in that equation, I'm still a new scientist, but how better scientists have come up with the isotope. That's how they figured out basically most of the isotopes, is they did mass spec on it. So that's pretty cool. All right, moving on. So you can have a mass spectrum from that. If you have a sample of chlorine, you can separate that sample of chlorine by its isotopes on this method, using this method, because you see how you'd have a spike for chlorine 37 and a spike for chlorine 35. And in a real mass spectrum, chlorine 36 might be like that. Chlorine 38 might be like that. You might have little tiny dots over here where you have anomalies, maybe a couple of atoms. It's like nothing. So we really don't consider that to be useful in scientific methods. And those will not be stable anyway. Once you put them through the detector, they'll disintegrate eventually, because their half-life is not very long. So hope that part makes sense, and that's how you detect isotopes. Okay. Next thing we're going to cover is the mole, right? So the chemist doesn't. Now, the mole is a large number, like I mentioned, and to cut to the chase, it's this number. It's Avogadro's number. So Avogadro is a scientist, and he came up with this number using his equations. I'm not going to go into that, but he came up with, okay, that was bad. He came up with Avogadro's number as 6.022 times 10 to the 23rd. So this is Avogadro's number. And basically what this means is that 1 mole of, anybody have a question? No? Okay. So Avogadro's number means that 1 mole of anything is an Avogadro's number of that substance. So you can have a mole of people, a mole of trees, a mole of atoms. We're going to talk about mostly atoms and molecules, but you can have a mole of anything. So it's just a chemistry-derived term, meaning an amount of something, and one of these units is an amount, that big number of particles, 6.022 times 10 to the 23rd. So good questions. You can put this in the chat. So do you think there are a mole of trees on Earth? Think about that. So it's that many. So that's 6 and about 23 zeros. Oh, also, Leslie, I just see your messages, okay? That's fine. Spartacus, you don't think there is, meaning, do you think there's more or less than a mole? You think there's more than a mole? Okay. More, all right, all right. Grass, I might believe that. Okay, okay. All right. So the answer to that is no. There is way less than a mole of trees on Earth. So this number is huge. And think about all the forests, and well now it's definitely less because like the Amazon caught on fire and Australia caught on fire. So not a very good 7 or 8 months for us, for Earth. But we're getting there. And pandemic, we'll get there eventually. Let's just skip 2020 and we'll move on to 2021. All right. So next, so do you think there's a mole of insects? People say maybe insects, maybe, right? Blades of grass, maybe, some of you. But in actuality, there is way less than the mole of insects, way less than a mole of blades of grass. And Spartacus just said sand, maybe, but there's actually way less than a mole of grains of sand on Earth. Damn is right. So I'll explain this. The mole is so big. And think about this, sand, I don't just mean like beaches. It's beaches, it's the desert. The Sahara Desert is bigger than the United States. And it's like miles deep with sand. You have the bottoms of the ocean, which is 75% of the surface area of the Earth. The bottoms of that, the sand everywhere. South Jersey, there's no dirt, it's just sand. And most islands are just sand, but you get the point. It's a shitload of sand, right? But a mole, to get a mole of sand, or I'll explain it this way. So there is about 3 times 10 to the, what is it? 18th, that's what it is, 18th. There is 3 times 10 to the 18th grains of sand on the planet, approximately. It was somebody's PhD thesis to go and count every single one of them. So there is that many. Avogadro's number is 6 times 10 to the 23rd. So, oh, you multiply it by 5. No. You multiply it by 100,000, or actually technically 200,000. 10 to the 5th. So there is 200,000 times less grains of sand on Earth than a mole. That's crazy. If you were to multiply the grains of sand on Earth by 200,000, which would encompass the Earth miles deep in sand, and it would be larger than the Earth in sand. It would be like covering Jupiter with sand. It would be a mole of grains of sand. That's crazy. So let's take this into perspective of how small an atom is. What did I say about a mole of carbon before? I said a mole of carbon is 12 grams, 12.011 grams. You could fit it in your hand and you won't even realize it's there. So think about the size comparison between a grain of sand and an atom. It's not even comparable. The atom is so infinitesimally small that a mole of most molecules can fit in your hand. Even something like iron. A mole of iron is 55.8 grams. That's nothing. You can fit that in your hand. And that's Avogadro's number, 6.02 to the 10 to 23rd particles of that element. And meanwhile, sand, not even close. Somebody followed up with, what about bacteria or single cellular organisms, or cells, for that matter? And yeah, I think there are at least a mole of cells on Earth, definitely. I'm not sure how many, but we can Google search that. Let's do that. I don't want to take too much time, but how much bacteria? Well, is there a mole? Is there a mole of bacteria on Earth? I don't want to read that. Whatever. Okay. Let's say there is. I don't want to read anything. All right. So, good. Is there any questions on that size comparison? I hope I blew your minds so far. No? Okay. So next, we know that what the mole is. We know what the mole is. Okay. So we can say for the molar mass that 1 mole of an atom is the molar mass or the average atomic mass in grams of that element. So 1 mole of carbon is about 12 grams, 12.011, and that is 6.02 times 10 to the 23rd atoms. And from this, we can have conversion factors. So we can use the moles per atom and also atoms per mole. And we can also use the molar mass as a conversion factor. So these are common conversion factors. And I'll just cut to the what I just did. There we go. So I'm going to cut to the chase. Let's do these. Okay. So how many molecules are in 2.35 moles of HCl? Okay. So HCl. Now think about what the question's asking. It's saying how many molecules are there. So we know that there's 2.35 moles. Also keep in mind, I was talking about atoms before. The reason why I was talking about atoms is because we were talking about either chlorine or carbon or singular elements. The same rules apply to molecules. A molecule of HCl, a mole of that is still a mole of each one. So a mole of Na3po4 is actually encompasses 3 moles of Na, 1 mole of P, and 4 moles of oxygen. So I hope that makes sense, but we'll get there. All right, so you have 2.35 moles of HCl, and we know, we're asking for the molecule, so we know that there is 6.022 times 10 to the 23rd molecules in 1 mole. So to figure out how many molecules there are, you multiply together and you get, it's going to be a number. It's going to be a number, 13 something. So let's just see. Here we go, 14. So 1.4, if you could see that. So it would be in proper scientific notation, 1.41 times 10 to the 24th molecules of HCl. You notice how I didn't use the molar mass of HCl or anything. It's not important for this question because I'm just asking about molecules. And you have moles. If it was, the answer, what I'm trying to say is, the answer would be the same if it was water or CO2. It doesn't matter in this case. How many moles, how many molecules are in X amount of moles of whatever, the answer would be the same. Not depending or independent of what compound we're talking about. Okay, next one, how many moles are in that many molecules of Na3po4? Again, the molecule or the compound doesn't matter. If how many moles of this many molecules are of Na3po4, if it was HCl, it would be the same. Did somebody ask a question? Oh, wait, there's questions. Oh, you guys good? You guys good? Gio and Brandon? Yeah, we're looking for mole. Yeah, okay, cool. All right, cool. So we can go the opposite way in this case. So we have the 4.277 times 10 to the 23rd molecules. We're looking for the number of moles. And we know the conversion factor, that 6.02 times 10 to the 23rd is 1 mole. So just like we did unit conversion yesterday or 2 days ago, 1 mole over 6.022 times 10 to the 23rd molecules. Molecules cancel out, and you get whatever this is divided by that, maybe 0.6 or something. So what do we get? We get 0.7102 moles of Na3po4. So does that make sense? Is there any questions? No, we're good. Okay, cool. So now we can use the molar mass as a conversion factor. So we can say that for, let's say for aluminum, if you look at the periodic table, aluminum is right here, and aluminum has 13 protons. And more importantly, for our topic we're talking about now, the average atomic mass is 26.982. So 26.98. So 26.98 grams of aluminum would be 1 mole of it. And 1 mole of it would equal 6.02 times 10 to the 23rd atoms of it. So this is the triple conversion factor that I'm trying to get to. That's like the whole enchilada with this idea. And with carbon, same thing, 12.01 is 1 mole, and that's a mole of atoms. And then you see how the mole of atoms are the same. It doesn't matter which element we're talking about. The number of molecules or atoms in that mole is exactly the same, because the Avogadro's number, the mole, is just an amount. So we can do that. So what is the molar mass of carbon? We can look at the periodic table and see that it is 12. What is the mass of 0.67 moles of carbon? So you know that the molar mass of carbon, meaning the mass in grams in 1 mole, is 12.01. If you multiply that by 0.67, you're going to get 0.67 moles. So you get around 8 grams. Then you can say, you can use the conversion factor again. Wait, I just want to, you see the answer if we do. So how many moles are in 45.67 grams of carbon? So we know the molar mass, and we can use it as a conversion factor again. I don't know why I just wrote the 5 like that. 45.67 grams, and we know that 1 mole is equal to 12.01 grams. Grams will cancel out, and you just do 45.67 divided by 12.01, and you get 3.8 moles. So we can also use the molar mass as a conversion factor as the grams of one element per mole of that element, per mole of that element, per mole of that atom, per mole of that element. Fine. Okay. Does that make sense? Good. Okay. So here is everything I just said conceptually. Now take a look at this. If you memorize this, you are good with all type of molar conversions. And it makes perfect sense. So let's start with grams. You have a grams of any sample, right? Let's say water. Let's say you have 100 grams of water, and you want to convert that to moles. If you think about it, and I wrote up here, remember to make smart calculations. What I mean by that is think about the size of number. It doesn't just relate to chemistry. This relates to calc or to physics or to whatever class you're taking that has to do with numbers. Think about the size of the numbers that you're calculating. Is your answer supposed to be bigger or smaller than one of the numbers you have? That can help you troubleshoot your mistakes. So for grams, we have 100 grams of water. If we're trying to convert to moles, is that number going to be bigger or smaller? Somebody can answer that on the chat, maybe.
From what to what?
Oh, from grams to moles.
Moles is always going to be bigger. Wait, no.
So I'm talking about the
moles
actual
is going to be
number.
smaller.
Yes, good. So moles are going to be smaller. So 100 grams of water, I'm going to do that in my calculator.
Is a fractional mole.
Exactly. Well, so 100 grams of water, the molar mass of water is 18. It would be 5.55 moles. So the idea is that if grams is 100, or a big number, moles is going to be smaller. It's going to be a smaller quantity. So we always have to divide. If you're getting a big number to a small number, you divide. And you're dividing by the molar mass. So you see how this works. Grams divide, and this is the conversion factor we're using for this section. Atomic weight or molecular weight, otherwise known as atomic mass, all interchangeable terms for our sake. And you divide grams by molar mass, and you get moles. If you want to go from moles to molecules, now someone tell me is what's bigger, moles or number of molecules? What's a bigger number? Molecules. Good job, Sarah. So obviously molecules are atoms because we're dealing with 10 to the 22nd, 3rd, 4th, or whatever. Meanwhile, moles are only single digit numbers. Maybe you might see 10 or 15 moles at most, but you're never going to see 10 to the 23rd moles or anything like that. So in that case, to go from moles to atoms, we are multiplying, get it, multiplying by Avogadro's number, or the conversion factor of atoms to atoms per mole, or molecules per mole. And then going backwards, we do the opposite. Atoms is a huge number. We're never going to multiply atoms by anything. We're always going to be dividing it to get to moles. And then going from moles to grams, like we talked about, this is just the opposite. Moles is smaller than grams, so we're going to multiply by our molar mass to get to grams. So does that conceptual idea make sense? And if that makes sense and that clicked for you, basically me ranting was all about there's 2 conversion factors and there's 3 types of units you can get for each substance. You can have the grams of the substance, the moles of the substance, or the molecules of the substance. And using those 2 conversion factors, you can go back and forth between all 3. That's basically it. All right, so let's continue. Let's try to figure out the mass of carbon atoms. Or I could just say what's the mass of 9.86 times 10 to the 23rd carbon atoms. I just wrote that weird. I don't think I did that. I think the textbook did that. So I'm not stupid. Okay, so let's figure this out. Why don't I just click that? So we have 9.86 times 10 to the 23rd atoms. We want to get to mass, to grams. So remember that flow chart. Atoms were on the right side, moles were in the middle, and atoms were on the left. Or sorry, grams were on the left. We have to go through, we have to get to moles, then we have to go from grams to grams. So moles to grams. So for atoms, we know that in general, 6.022 times 10 to the 23rd atoms is 1 mole. We know that. And also, and then this would cancel out. And also, at this point, we would have the moles. It would be probably a little bit more than 1.3 or something. And then we know the molar mass of carbon, because in this specific problem, we're talking about carbon. So we know that 1 mole of carbon is 12.01 grams. That's 1 mole of carbon. And in case you lost me on where I got this from, it's from the periodic table. So you have the top number and the bottom number. The bottom number is the molecular weight or the molar mass. And the top number is the number of protons. Okay, so then we cancel out moles of carbon, and we successfully converted. Good morning. So we successfully converted from, you can't see that. You can successfully converted from atoms to grams, and our answer is, here we go. Our answer is 19.7 grams of carbon. So this is very similar to Monday, right? We're just doing it we're doing unit conversion with chemical things instead of converting from quarts to milliliters and all that nonsense. Now we're doing it with chemical quantities, and this skill is gonna be useful for a lot of problems and a lot of chapters moving forward in the class. So if you have any questions on it right now, you could ask me, or later too, but if you have any questions, now's a good time. Anybody? No? Okay. All right, so let's do more. So what if we have molecules? Okay, so before, in this example and previous examples, we were talking about just carbon or just hydrogen or singular elements, singular atoms, or singular elements. What if we have molecules such as Na2SO4, otherwise known as sodium sulfate? What do? But really the same thing applies. All we need to do is we need to find the molar mass of, instead of just one element, the entire molecule by adding the individual molar masses of each atom. So that's get it? So that was a bad joke. See, SO. So a good one is, what's a good joke? What's a good chemistry joke? Oh, why can you never, is there anyone named Adam in this class? I don't think so. But why can you never trust anyone named Adam? And the answer is because they make up everything. Get it? Okay. I'm sure a lot of you are like shaking your head like, no, stop. Just keep teaching and stop with the jokes. Okay. So the molar mass of Na2SO4. So simply what you do is add up the molar masses of each individual atom in the compound. So Na, let's look at the periodic table. Actually, no, I don't know. I just know it. So Na is 22.9. There are two of them, right? Na2. So this subscript 2, we didn't really see compounds yet, but the subscript 2 means that there's two of the element previous to it. So 22.9 times 2 is going to be around, let's just round it. We can round it to 23. That'll be 46. Then for sulfur, sulfur is 32.06, and there's just one of them, so that's 32.06. Oxygen, there's 4, 04. So each oxygen is around 16. And in your textbooks and in your periodic table, it says 15.997. That's okay. Something like that is that close to a whole number, you can definitely round to the whole number. And we have 4 of them. Times 4, you get 64. Well, I don't know why I just wrote a 3. Okay. Okay. So times 4 equals 64. All right. So if you add all of these together, it would give you the molar mass of 1 mole of Na2SO4, and it would be around 142 grams per mole. That would be the answer. Yeah, so you basically add up the molar masses multiplied by the number of atoms of each element in the molecule. That is essentially how you find out molar mass. So now you know how to figure out the molar mass of any compound on the planet. So you can put that, or any planet, you can put that on your resume and say like, oh, I can calculate molar mass of anything. Which it's not like too difficult because I taught it to you in like 5 minutes, but it's still, most people can't do that. Most people who never took chemistry. Okay, cool. So now we have that. Let's do more molar mass practice. So I will let you do this. So I will give you, I'm thirsty. I need to get water. So I will give you 5 minutes. Everybody still, hopefully no one fell asleep or is watching YouTube or on Facebook. But I will give you 5 minutes. So it's 10:18 now. I'll give you until 10:23. And in your notebooks or wherever, do these practice problems by yourself. And for parentheses, so before we start that, can someone tell me what you do with parentheses or what you think you do? So how would you figure out, you can just talk through it, how you would find the molar mass of MgNO3 2? Anybody want to take a shot at it?
Distribute.
Yeah, sure. Adnan.
Distribute.
Oh, distribute. Yes, that's what you said. So exactly. So what would you distribute?
You distribute the 2 between the nitrogen and oxygen.
Perfect. All right. Good job, Adnan. So you would distribute this 2. So it would be 2 nitrogens, and then you would have 2 times 3 or 6 oxygens. So that would be your answer. That would be, you would add that to your molar mass. Okay. So I'll give you now 4 minutes. I'll give you until 10:23, and I will be right back, and we can continue, and then we can go over it. Okay. And you feel free to talk to each other too. So I'm going to be right back. I just need to get a drink. back.
Can we just round to whole numbers to make it a little faster?
Yes, but in some cases you can't. So it's a good question. Now,
No, I mean just for this.
oh yeah, of course, yeah. But for things like when you deal with chlorine, you don't want to round chlorine because it's 35.45. So rounding it would, if you have two chlorines that you're already off, if you round it down to 35, you're already off by like 1 unit. So that's not very good. So for most elements you can round, but if you're around, if the molar mass is 0.4, 0.5, 0.6, 0.7, even 0.8, it's not good to round. But yes,
I get what you're saying.
okay. All right, 1 more minute. Okay, cool. So everybody got it, hopefully. All right, so we're gonna go over it now. So I'll do this quickly. Where's my pen? There it is. So I think, are the answers here? Let's see. Oh, not. No, whatever. All right, so H3P, we'll do Mg first. So magnesium, what's the molar mass of magnesium? Let's see. So it's 24.3. So you have 24.3 plus nitrogen, like we said, we distribute. So there's 28 plus 6 oxygens would be 16 times 6. And then whatever you get there. And what's the answer for this one? Anybody want to tell me?
I got 148.
Okay, that sounds right. 148 grams per mole. Okay, next, H3po4. Hydrogen, there are 3 of them. Each one has a molar mass of 1, so 3. Phosphorus has a mass of, I believe, 30.98. Let me just double check. Phosphorus, oh, 30.97, excuse me. So I could put 31 plus 64 because we have 4 times 16. And what does that equal to? 95, 97, right? Yeah, 97, 98. 98 grams per mole. Cool. Next one, CH3COOH. So this is acetic acid. So what we can do here is 12. Let's add up all the carbons. You have 12 for this one, 12 for this one, so 24. Plus 4 hydrogens, which is 4, plus 2 oxygens, which is 32. And you get 36, 50, 60. Wait, can you guys see my cat on the chair? If you see my video, she's on the chair. Okay, Chris, raise your hand. What's up, Chris?
Why is the oxygen separated and not
Oh, because
O2?
good question. So, oh, the cat phases in and out. Yeah, it's because of the background, probably. But she's there. Anyway, so to answer your question, that's because acetic acid is an organic compound. And in organic chemistry, a lot of times they don't like to group together all the oxygens and hydrogens because it helps with the reader understanding how they covalently bond together. So this would help me if I were writing the structure for it. CH3 would be CH3. C means that it binds to another carbon. OOH. In organic chemistry, if you see COOH, that means it's an acid. So you have a double bond to one oxygen and then an OH group like that. So it helps structurally. It's called the condensed structural formula, and it helps you with organic compounds mostly determine the way they bond together. So that's a good question. Okay, so we'll do this. What'd you get for? Well, I guess we'll just say the answers for this one. So anyone want to tell me what they got for this? PbNO3. So I'm gonna pull up the chat. Where's the chat? There it is. Okay, so what about PB? Barticus is not trying to finish all of them. I'm sorry. 331, that sounds right, because PB is 207. So 331. Definitely practice these on your own. What about NH4 2SO4? 132? Sounds right to me. 164. Okay, we'll do this one. So 14 plus, or not 14, sorry. We're distributing. So 2 times 14 is 28 plus 8. And you have that. Then you have plus sulfur, which is 32, about 32. And then 64 for the 4 oxygens. And that is 96. What is that? 64 plus 32 plus 8 plus 28. 132. Awesome. So 132 is correct. What about the gallium 2 and then the sulfite? What do you guys get for that? 379. That sounds right, because gallium is a big element. 379. And then what about the Cl2 F2? It's 35.45. 35.45 plus 12 plus 2 fluorines, which is 19 and 19. That's 120. Good, 120.9. Awesome. So 120.9. All right, good. I think we get the hang of molar mass. All right, good. So here's another example. You could do this example on your own. And I usually, if this was an actual lecture, I'd give you a break. Kitty break is my cat. But no, because we're gonna keep going. So let's talk about the periodic table. That's what we're gonna talk about for the remaining part of the class. So the periodic table is separated into 3 classifications of elements. Those will be metals, nonmetals, and metalloids. So metal, we'll talk about each one specifically. So metals, they are on the lower left and middle parts of the periodic table. I just like to say the general left side. So if you're looking at the periodic table, this is a great one because it's color-coded. There on the left of this is a staircase. We call it the metalloid staircase, which starts at the left of boron, goes like this, if you're following my cursor, all the way down like that. And anything to the left of germanium, like anything to the left of that staircase, well, everything touching that staircase is a metalloid, but everything to the left of that, meaning all of these elements that say P down here, that P is post-transition metal, and everything to the left of that is all metals. The lanthanides and actinides are all metals. All of these, sodium, lithium, all metals. The nonmetals are here. The metalloids are along that staircase. So, and there's one exception, and hydrogen is that exception. So hydrogen is a weird element, and it fits some things, but doesn't fit some other things and trends in the periodic table. One of those trends that it fits, which we'll talk about later, is its valence electron number is 1, just like every other element in group 1A. But it's not a metal, and there's other things that it doesn't have similar properties to all these other elements. The reason why that is because, think about it, the periodic table was made by people. And this is our best interpretation of how to organize the periodic table. In some cases, there's like, yeah, we didn't know where to put it, so we're just going to put it which makes the most sense, but it might have some flaws. Because the way the universe was made, however you want to think it was made, it's just, to us, we're just observers of it. And this is our best way of just taking in everything we can figure out and putting it into a way that human beings can understand. And our understanding isn't the greatest understanding in terms of, we're still learning new things, groundbreaking things. There's still most things we don't know. And this is everything we do know, organized to our mind can comprehend it the best. Doesn't necessarily mean it's perfect. So hydrogen is weird. Lanthanides and actinides, they are metals, but they are on the bottom. They basically just fit in here. So the reason why they didn't put them there is because the page isn't big enough. That's actually why, because it wouldn't fit an 8 by 11 page. So you have to put it on the bottom and just say, oh, it belongs in there. Okay, I just made that up. I think it's not because of the page, but it doesn't make a lot of sense. They just put it there because there's no scientific reason they're trying to get at. But anyway, so the metals, they are good conductors of heat and electricity. They can be malleable, they can be wires, they're shiny a lot. And the most important thing, chemistry thing, is they tend to lose electrons when they undergo chemical reactions. This means they become cations. Get it? Cations. But they actually become cations, which means they're positively charged. So a key concept of this course is in the beginning, is to know that, to understand what happens when electrons are lost and gained. So if you lose an electron, you are losing negative charges. If you're losing negative charges, you are becoming positive yourself. So that's where we get this cation term as meaning positive, and then anion means negative. So positive, anion equals negative. All right, so there are a lot of metals. Then you have the nonmetals. So the nonmetals lie on the upper right side of the periodic table. So they are on, starting at carbon, phosphorus, selenium, iodine, all of that to the right. All of that to the right is nonmetals. So you have this group and then parts of these groups. They're all nonmetals. Not many of them. There's maybe, I don't know how many, there's maybe 20, or 15. So, 17. So, yeah, so nonmetals, they're not good at conducting electricity. They're not very malleable. If you have a solid nonmetal, such as you have solid sulfur, phosphorus, it's just like a brittle powder. It's not really strong or anything. And some of them are solid at room temperature. Bromine is a liquid at room temperature. Most of them are gases at room temperature. And a lot of these nonmetals form diatomic gases. So a lot of these gases, and the reason why they form diatomic gases, well, first of all, diatomic gas is what it is, diatomic, meaning two atoms. So hydrogen gas, it's not just a singular hydrogen floating in air. We don't breathe in singular oxygen either. They're diatomic gases. This makes them very stable. This makes them nonpolar. It doesn't have any charges. It doesn't want to react with anything. And we'll go over that more when we talk about valence electron theory. But you have these main gases that are nonmetals and they form diatomic gases. So yeah. Next you have the metalloids. And the metalloids, they're kind of exactly what they sound like. They're in the middle, metalloid-ish. They're like metals and they're like nonmetals in some ways. They have mixed properties of conductivity and reactivity. And that's why they're classified as semiconductors, while metals are classified as just plain old conductors. That's why silicon and gallium and things like that are, not gallium, no, germanium, sorry, that's what I meant. So like germanium, they're used a lot in computer chips because they're semiconductors. They don't conduct all the electricity. You could actually, with resistors and capacitors, modulate how much electricity goes through and whether to turn it on or off or to change the voltage. And they're good at that kind of modulation. Whereas a copper wire is either on or off. It either conducts fully or there's nothing going on. So if you put a current through it. So that's why semiconductors and metalloids are important for a lot of technological things that have to do with modulating voltages and different electrical currents. Okay, so is there any questions up to now about that? Or about anything? No? Okay. All right, cool. You can click the raise hand button if you have a question, just like Chris did before. All right, so a periodic table. Periodic table can be divided into main group elements and transition elements. This part is important. So here's what we're going to talk about. main group elements, they have this group naming called A, either 1A, 2A, 3A, 4A, etc. So here's how it works. Going from the left, group 1 is group 1A. And the reason why we call it this is because, I'll cut to the chase, is because this main group element number, 1, 2, 3, 4, 5, 6, 7, 8, are the number of valence electrons in that entire group. And that will help you determine the number of valence electrons when you need to for charges or for reactions and things like that, or just to do Lewis structures and things later in the course. But the main group elements are, the way I like to think of them is the ones that are taller, the ones that are taller. So group 1A, 2A, we skip the middle section completely. Those are your transition elements. They have a varying number of states, and that's what they're called, transition elements. They always transition from having maybe 2 valence electrons. Some of the atoms have 3 valence electrons, 4 valence electrons, and there aren't any rules when it comes to the transition elements. There are a few, but in general, they can have a varying number of valence electrons and reactivity. So you can't classify them as these are exactly +3 all the time. And then you skip those and go to the rest of the main group elements, 3A, 4A, 5A, 6A, 7A, and 8A, which all have that whatever A number of valence electrons. So does that make sense? You have transitions, which are here. They don't really follow any type of naming scheme, or they follow their own naming scheme when we get to that. And you have main group elements, which are on the top, which they have a distinct properties that they don't change the number of valence electrons they have, and their valence electron number is dependent on what group they're in. So 1 is 1, 2 is 2A is 2A, 3A is 3. All right, then the other groups you have within this section. So I do expect you to know a few of them, and I will circle those group numbers. They have specific names. So 1A, this is called the Alkali Metals. Group 2A is called the Alkaline Earth Metals. Now those names can get confusing, but the way I think about it is the longer name comes second. Like it's longer, 2 longer, I don't know, 2 longer. Alkaline Earth Metals, it's a longer name, 2. Alkali Metals. Then we skip all the way over here. These have names, these groups, but there's so many different things going on in terms of, oh, you have nitrogen and phosphorus, which are common non-metals. Then you have 2 metalloids, and then you have bismuth. So there's a lot going on there. We don't really call this column a specific name. Same thing with 3A and 4A, and even 6A. But 7A, we call the halogens. Halogens. And then 8A, we call the noble gases, because they're very noble. And we'll see what that means right now. So noble gases, and here's a good little picture of noble gases. They're very noble, and what that means is they are not likely to react with anything. They're mostly very unreactive. And the reason why they're unreactive is because they have 8 valence electrons. And that happy number of 8 means that they don't need any more valence electrons. They don't want to lose valence electrons, and they're happy with the number of valence electrons they have. Therefore, 8 is their number. And they're happy, and they don't want to react with anything else. And I kind of think about it as, you know, like if you ever go to London, I've never been to London, but like you see those guards, those like noble guards, for like the Queen guards or whatever, and you can like take pictures with them, and they don't really move. They don't say anything. They don't do anything. They're very noble. So they're not going to react with any of your shenanigans, or if you like pretend to like hit them or something, then they might react. But normally they don't react with anything, and they're just noble guards. So I think of noble gases as the same way. Then you have your alkali metals. Alkali metals are in group 1A, and they're kind of malleable, and they're pretty reactive as well, or not as well. They're reactive unlike noble gases. because they only have one valence electron, and that valence electron wants to be lost from the metal. And they explode when they come in contact with water. That's pretty cool. So I do have I ordered online, I'm thinking on eBay, like a $10 thing of sodium that I never got a chance to do it in one of my classrooms, but I want to do it live. I don't want to do it on like a video, but next time we get into a classroom, not us, but like next time I get into a classroom with another class, I'm going to do this on the table. Probably not allowed, but I don't care. It's cool. To put some sodium in like a dish and then just put water on it and watch it explode. A small amount, but that's my rebel chemistry professor nature getting the best of me. So they explode when dropped in water. So that's pretty cool. Then you have alkaline earth metals. So alkaline earth metals are in group 2A. They're fairly reactive, not as reactive as group 1A. I hate reading directly from the slide, but that's very nicely worded. But you have other ones like calcium, and I don't know why the list isn't there. But anyway, those are these. Beryllium, not really beryllium. Beryllium's weird, but the main ones, you have magnesium, calcium, strontium, and barium. Those are like the main ones we talk about. All right, so, well, beryllium's there too, but beryllium sometimes likes to form covalent bonds, which is weird. It doesn't really form ionic bonds like the rest of them, but it's still considered an alkaline metal, an alkaline earth metal. Then you have halogens. Halogens are the most reactive element in the periodic table, or element type. So fluorine, to be more specific, fluorine is the most reactive element. And that's because it has a very high electronegativity, which we'll talk about in another class. And also it's because of its valence electron number of 7. So 7A, number of valence electrons is 7. That means it's 1 away from being a noble gas. It's 1 away from being really, really happy. If you're so close, like let's say you ran a marathon and you're near the end, you see the finish line, you're going to do your final sprint. You're not going to start to jog, like you're not going to jog anymore. You're like, oh my God, the finish line is right there. All this pain can finally stop. You will do anything to get to that finish line if you really want it that bad. Fluorine wants it that bad. And also the other halogens want it that bad. They will react with anything to get that final valence electron, so they'll have a noble gas electron configuration, which is the goal of a lot of these elements, is to have 8 valence electrons when they react. But we'll talk about this in another class. Oh, maybe now. I guess we'll talk about now. Oh, we're almost done, actually. Okay, so is an intro to ions. So I talked about cations and anions, right? So cations are positively charged, and the metals like to form cations. So they lose electrons to become positively charged. Then you have the anions, which are negatively charged, and they are mostly non-metal. So these are really key phrases. If you memorize these phrases, you're good. Metals lose electrons and become positively charged. That encompasses everything. Non-metals gain electrons and become negatively charged. This is when they're in reactions with metals or making bonds with metals. So if a metal and non-metal bond together, let's do an example of Na and fluorine. Initially, they are neutrally charged. It is a common misconception. I've seen professors teach where, oh, you have the sodium and the fluorine, they come together and they make sodium fluoride because of their positive and negative. No, that's not true. They don't come together because of their charges. They come together in close proximity randomly, just by being in the same solution, being in the same vicinity. Sodium, because it's in group 1A, has 1 valence electron. Fluorine, being in group 7A, has 7. When fluorine comes in close enough contact within a few angstroms, which is a very small unit, it's smaller than like picometers, or it's a little bit bigger than picometers. When they come in close contact with each other, because they're in the solution at some concentration, what will happen is fluorine, since I mentioned before, he really wants to gain that last electron. what happens is fluorine will go up to sodium and be like, yo, bro, I need 1 electron really badly. Sodium will be like, oh, damn, I really need to get rid of my electron really badly because I'm a metal and I lose electrons to become positively charged. And fluorine's like, yo, I knew the definition of that already. You didn't need to teach me. But fluorine will be like, all right, I will take your electron and you'll be happy and I'll be happy. And that's exactly what happens. Then, this is the key part of an ionic bond, of an ion. The transfer of electrons induces the positive and negative charge. After sodium loses this 1 electron, it becomes positively charged. After fluorine gains that electron to have 8, it becomes negatively charged. The transfer of electrons induces that charge, which brings them together. So yeah, technically, maybe if someone said like, oh yeah, the positive and negative, they go together. But the most important thing of an ionic reaction or an ionic bond formation is how that happens. And the transfer of electrons induces the charge, which causes them to go together. Some people think it's the other way around, but it's not. Okay, so I hope that makes sense. Is there any questions on that concept? No? Yes, no, maybe so. No, pretty good? Okay, cool. Hopefully you're still listening.
You're saying that when atoms combine together, they don't have an exact negative I mean, they don't exactly lack a charge.
So initially they're all neutral. And then when they come in close proximity, that's what causes electron transfers, electron sharing, with covalent bonds. But initially they're all neutral until they come in close contact just via the solution, via the liquid they're in. But that will happen, since there's billions of them, it does happen really quickly.
By neutral, you mean like the
Neutrally
ion,
charged.
or like,
So by neutral, I mean the protons are initially the same number as the electrons.
okay.
Okay. Actually, I have to take a call real quick. This is my realtor. This might be important. So I'll mute my mic and just meditate. If you have any questions, ask me in like a minute.
Okay. Anyone here good at calc?
Yeah, what's up?
I'm trying to do homework and like I for the life of me cannot figure out how to get the cotangent of pi over 3.
It's just 1 over the tangent of pi over 3. Yeah, so like
Isn't
tangent of pi over 3 is
isn't it 1/2?
no, that's the cosine. So the tangent of pi over 3 would be
Okay, sorry about that. I'm back.
never mind.
Tangent of pi over 3. What are you talking about?
Yeah, somebody had a calc question.
Oh, I'm good at calc too.
Here, you can message me and I'll type you the answer.
The square root of 3 over 3.
Oh, are you guys doing like calc homework in the middle of this?
No.
Oh, sure. Okay. Well, that's fine. Whatever. If this is too easy for you and you do calc homework.
Well, I just failed chemistry, so like I know the first unit pretty well.
Yeah, I guess so. Yeah, a lot of you are retaking it, I'm assuming. So the first couple of units shouldn't be too bad, but a lot of you aren't taking it, so I have to teach at this pace. So yeah, do whatever you gotta do, and it's chill, whatever. Okay, let's move on to charges. So I hope you understand that. This is a good table that has all the charges that I expect you guys to memorize, and it's pretty easy if you look at the trends. So hydrogen and group 1A along with hydrogen, they all have +1 when they become ions. And this is when they become ions. So when they lose their electron or electrons. So group 1A, they have 1 valence electron and they end up losing it and they become +1. Group 2A has 2 valence electrons and they become +2. Group 3, remember the transition metals, it varies a lot. Group 3A, just aluminum. So it's just aluminum for this one, because in group 3A, you have boron, and then you have these post-transition metals here. Aluminum is the only one in group 3A that holds a specific charge, and it happens to be +3, and that's for the metals. Then if you go the other way, group 7A is nonmetals, is halogens, and they have a -1 charge, because what they're doing in the example I used before is for fluorine, when they gain that 1 electron, they become -1. So they're only going to gain 1 to get to 8. For group 6A, they're gaining 2 electrons to get to 8. So it becomes O2-, S-, etc. For nitrogen, also phosphorus, this is true also. I don't know why it's not bolded in. And they have 5 valence electrons. They need to gain 3 more in order to get to 8. So that's why they have a -3 charge. When they do gain those 3, they get to 8. And we'll be learning more about this next chapter on, I think, Wednesday. We're going to talk about naming and all that stuff. And exactly the different types of ionic bonds that form. So is there any questions on that? I know I went through it pretty quickly, but there is a clear trend that you should know. And it's not, I don't think it's too bad. Okay, so let's think about this and we'll answer these, and then we're almost done. The rest of the chapter, even though there's 76 slides total, a lot of it's redundant. Let me see. Yeah, a lot of it's redundant. And the last parts of the experiments we'll go through quickly. I don't think I'm not gonna test you on that. Okay, so think about it. What is the most likely formula from the following molecule or atoms? All right, so potassium and chlorine. So let's look back here at the periodic table. Potassium is K right here. Chlorine is Cl's right here. So can anybody tell me via chat or talking what would be the best formula for that? Why can't I get the chat window up? There we go. Yep, good. KCl, perfect. And the reason why is because K is +1, Cl is -1, so KCl balances out perfectly. Another thing is, I didn't mention it specifically, but ionic bonds, they need to have equal and opposite positive and negative charges for them to balance out and equal 0. So, yeah. Next is going to be, oh, there's a chat, something in the chat. Let me pull it up. Oh, Ca. Yeah, Ca and oxygen. Okay, so calcium and oxygen. So calcium is right next to potassium. Calcium and oxygen is right here. So what would be the correct formulas? Good, CaO, cal, right? And that's because of the same thing. You have calcium is +2, oxygen is -2, 1-to-1 ratio. Next is, I think, boron and sulfur, or no, bromine and sulfur. Wait, where am I going? Barium and sulfur, and then sodium and hydrogen. All right, so barium and sulfur. So barium is right here, sulfur is right here. Oh, wow, look at that. What's it gonna be? It's gonna be, yep, Bass. Exactly, good. Where are the difficult ones? Sodium and nitrogen, there we go. So now sodium and nitrogen is gonna be a little bit more difficult, but still pretty easy. Oh, what did I do? Oh, come on. All right, so sodium is right here. Nitrogen is right here. Sodium is +1, nitrogen is -3. So what do you think the formula would be? Pulling up the chat window. Why is it not? Here we go. Good, Na3N. Good, that's because you need 3 NAs to cancel out with 1 nitrogen. Awesome, I think we're pretty good at this. Okay, so the rest, let me just go through it slide at a time. It's like kind of redundant because I took this from the textbook and the different sections were weird, and I just like spliced them all together. So we've kind of learned about that already, atomic mass and atomic number. or actually maybe we didn't talk about mass number specifically, but basically for each isotope, we learned about isotopes already. Wait, hold on. Oh, you guys made a group me? Good. Yeah, do that. Join a group me. Do you want me to join it or no? You don't have to. I'm used to being excluded, so it's okay. Prob's not. Thanks. Yeah, so I won't join it. That's just for you guys. Do that. What you want to do? I'll tell the TA to join it. So she'll be my eyes and ears. I'm gonna copy the link. Yikes. Yeah, yikes is right. All right. So I know what you're gonna do. I know what you're gonna try to do during the exam and stuff. I know. I wasn't born yesterday. Well, at that point, you might as well.
You might as well join us.
Might as well join it. Yeah, yeah. I'll see. I'll think about it. I'll think about it. I'll see how I feel about that. I told you guys to make groups, so it's kind of my fault. But I mean, it's good. You can help each other. That's fine. Like I'm just joking around. Like I don't really give a shit. Like you guys are fine. Make a group me. It's good for you guys learning. So anyway, isotopes. So we know the isotopes already. We know what they are. But there is a specific chemical symbol we call the nuclear symbol for each isotope. And it's a little bit different than a periodic table. So the periodic table, we have our proton number on the top and our mass number, atomic mass, or average atomic mass on the bottom. In this case, it's flipped, and they're not on the periodic table. But the periodic table, keep in mind, it's talking about each element at a time. So the abundance of each element, it's just talking about that element in general. These symbols are talking about an isotope or a specific atom of an element. So you can see that the mass number is actually on the top. The mass number is equal to the protons plus the neutrons, which I mentioned before. Protons plus neutrons is the mass number. Okay, so if that's the case, that's that. And that mass number varies with the neutrons. Your atomic number is Z, and that's on the bottom. And for neon, here's your 3 isotopes of neon, and they all have the same protons because it's 10. And then mass number varies based on the number of neutrons, increasing from 10 to 11 to 12. And then your chemical symbol is there. So the reason why I like this notation is because to figure out the neutrons, here's all you have to do. That's not a good line. So to figure out let's do that again. Figure out the neutrons. All you have to do is subtract. So you take the symbol and literally just set it up as a subtraction, and you get 10. Subtraction 11. Subtraction 12. And that's neutrons. So that's a cool little trick to figure out the neutrons from the nuclear symbol. So yeah. Okay, so we're not going to do this. That's too easy. Yay, good. We'll do it. Nah, we're good. All right. I'm being lazy, but like that's. So here, what is the atomic? We'll do it. Fine. What's the atomic number? I'm just hungry, so I get cranky when I'm hungry. I need breakfast yet. So what is the atomic number and mass number of nitrogen-14? So nitrogen-14, whenever it's in this notation, whatever 14, uranium-238, for example, that means the mass of the isotope. So this means mass. So if that's the case, that means you're going to have the mass of 14, and every nitrogen is going to have 7 protons. So the atomic number is 7. The mass number is 14. The neutrons are also 7, right? Because 14 minus 7 is also 7. So the answer would be, which one? A. Cool. So periodic table, we understand that. Something I didn't say specifically is that the groups are the vertical columns. So you have group, I didn't mention group, like group 1A, group 2A, but formally they're called groups. And then going across the periodic table horizontally, they're called periods. But honestly, periods are not too important unless you want to locate an element. There is no similarities between all the elements in a period, because these, you see, you have alkali metals, you have transition metals, you have metalloids, you have nonmetals. It just goes through everything. The only thing you have in common is that they go in sequential order of protons. Let's say for potassium, this is for period 4, goes from 19 to 36. So that's about it. Isotopes, we understand isotopes. Periodic law, I'm not really gonna talk about that. We talked about all that already. This is a good chart, good periodic table if you want to see more, but same thing. Let's go through these experiments quickly, and then that's basically it. So there are some key experiments that were used to discover these subatomic particles. And J.J. Thompson used a cathode ray tube to detect electrons. So what he did is he shot a beam, and they didn't know what beams were. They just knew they just shot light, or they shot a beam of, it was technically alpha particles, it was helium, but they shot it through a magnetic field. So a positively charged plate and a negatively charged plate on one side. Then when they shot it through, they saw that it bent towards the positive electrode, or positive metal plate. If that's the case, that means there must be something really negative inside the beam or inside those atoms. And we discovered that as the electron. But they didn't know what else it was. They just knew that, okay, there's something negative. They thought all the atoms were negative because of that. But no, it's because of the electrons moving around. That's why they went like that. They went towards the positive end. Then there's Milliken's oil drop experiment, where basically the same thing. He basically did the same thing, and it was just more complicated. And he figured out the charges. What did he do? He figured out the charge and the mass. So he had a sample. Then he had this pressurized thing that atomized the sample. So you have atoms in here, positively charged plate. They would go through the positively charged plate. You have radiation hitting them to ionize them. In other words, the radiation would kick off electrons and make them automatically charged. Then you have a negative plate, and they would see how fast they would drop, and if they would drop, and which way they would go, towards a positive or towards a negative. And from that, they can figure out how strong the charge is and what their mass is. So he figured out the mass of an electron and the charge of an electron from that. Now, mass of an electron for physics is important, for not for this class. Or maybe there might be homework questions using it, but it is right here, and you can Google it. And the charge of an electron, there may be some questions that use it, but let's say there might be a question, if you have 50 electrons, what's the charge? Knowing that the charge of one of them is 1.6 times 10 to the negative 19 coulombs. But that shouldn't be too difficult. Then you have, I don't even like Thompson. Thompson's plum pudding model. He's one of the first scientists to think, after Dalton, to think about the atom. So his model was, basically you just have an atom, and there's just everything, the protons, neutrons, and the electrons are just inside, and it's just random. Like a plum, I don't know what a plum pudding is, but it sounds disgusting. And that's what he thought it was. But that's soon to be not true by one of my favorite experiments. And the last thing we're going to cover today is Rutherford's gold foil experiment. So I know I'm going through this pretty quickly, but there's not going to really be any questions on the other ones. Rutherford's gold foil is important to understand. So up until this point, think about this. They thought Thompson was right, that an atom was a solid ball, a solid sphere that was positive and had these negative electrons in it, and they didn't even know about neutrons. They just thought it was a solid sphere. Rutherford made an experiment to definitively test that theory. He got a source of radiation of particles, and so this lead emitted alpha particles. Alpha particles are basically highly charged, or highly excited helium atoms. And he shot them out of gold foil, right? So if you think about this, you're like, all right, you're shooting one atom into another. Thompson would be like, oh, that's preposterous. It would do nothing. It would just bounce off. Because you have gold, it's just going to be a bunch of atoms of gold in sheets like that. So he shot these atoms through, these smaller atoms, these helium atoms. And Thompson, everyone would think, yeah, this is going to bounce off directly the way they came back. Duh. That's not at all what happened. What happened was 99% of them went right through with little or no deflection. They went right through the gold foil. So you could be thinking, they were like, no way, there's no way that happened. But they tested it again and it happened again. So they were like, all right, that doesn't make any sense, because how can a solid gold foil that I can touch, that I can feel, and I can't put anything, I can't put water through it, I can't put anything through it, light doesn't even go through it, but somehow these atoms go through it. That must mean that the atoms are mostly empty space if 99% of the particles went directly through with little or no deflection. So hopefully that makes sense. Then they're like, all right, some of them did deflect. If that's the case, that means there must be a very small percentage of solid material in the atom that allows them to bounce other particles off of it. And that's what we now know as the nucleus. So that is an atom, the nucleus is in the middle, electrons are on the outside, like that, like that. So that is our modern representation of the atom. Not very good drawing, but whatever. So to give you the idea, last thing we can cover, or let's look at his results. About over 98% went straight through, 2% went through, were deflected by large angles, 0.01% bounced off the gold foil. So his conclusion, the atoms are mostly empty space. Atoms contain dense particles that were in small volume compared to the rest of the atom, but large in mass. The reason why he said large in mass is because if you have a nucleus that is very small, and only 1% of the space, and it contains all the mass of the atom, since everything else is empty, it must be really large in mass, and it must be very dense. And it's mostly positive charge. So if it's positive charge, it's going to be all the protons are in the nucleus. So here's a good other representation of like that. What am I doing? All right. So basically, think about it this way. Right. Think about it this way. It's a baseball example. I love baseball. So here's a baseball example. The nucleus is equivalent. So let's take Yankee Stadium, right? Yankee Stadium is huge, fits 56,000 people. You take Yankee Stadium and you take all the mass of Yankee Stadium, thousands of tons of steel and whatever, and you put that mass into a penny, and you put that penny on the pitcher's mound. That is the nucleus in comparison to the rest of the atom. It is all of the mass of Yankee Stadium into a penny size in the middle of Yankee Stadium. That's what we're talking, that's the type of scale we're talking about here. It's so dense. And the density is what kind of makes the electrons move around it so much. It's an extremely dense particle in the middle, which kind of makes them have a very slight gravitational / charge pull towards the middle of the nucleus. And yeah, so that's what brings the atom together. So that's basically it. Is there any questions on anything I just went through?
Yeah, I have a question.
Yeah, what's up?
It's just kind of like theoretical, more like, but
Yeah, sure.
if you found a way to like to create another substance that was just as dense as the nucleus, do you think we could like recreate gravitational forces?
Black holes. They're
Is
very
that
dense.
what a black hole is?
Yes, on a grand scale. So a black hole is, they like to say, infinitely dense particle. I'm not sure how much I know about that, but it's extremely dense, and it's so dense that the gravitational pull is insanely strong that anything that goes near it, you know, gets sucked in.
Mhm.
It kind of makes a bend in space-time that, I'll draw it. Like normal, like our Earth has a gravitational pull, and it's kind of like, and to other planets, I mean, and it kind of like does this to space-time. So if you're here, like the moon is like here. So it kind of like, this divot in space-time makes it orbit around, and then the orbit doesn't really change because it's such a slight divot that it changes over time, but it takes millions of years. A black hole is like this. So if you get like here, you're done. You're falling right in, and there's no way out. So it's a very steep gravitational pull by a really dense object in the center, by like dark matter or whatever. And I think they made a black hole like for a split second. Let's look at that. So did scientists make a black hole? Here we go. So a scientist's tiny black hole brings the cosmos into the lab. So single-purpose quantum computers are helping physicists build simulations of the simulations. So yeah, that's for another time, I guess. But yeah, so hopefully that answers your question. So black holes would be that recreated, very dense particle that it gets really dangerous because then it just sucks us in and we die. But yeah. Okay, so any other questions? If not, then I will break you out into breakout rooms for chapter 2, basic homework 1. There's only one basic homework. Let's see, where is Moodle? NJIT.
Does alchemy have to do with chemistry?
Alchemy, yeah. So alchemy is like old chemistry, is like formulation and stuff. So alchemy is like medieval like.
Wait, so what's that
things.
thing where you make new? What's that thing where you make new elements, or like you try to take one element and change it into something else? I thought that was.
Oh, it's like alchemy. You're trying to make like convert metals to gold and stuff.
Yeah.
Yeah. So that's like alchemy. You can't really do that, but you need like, so you can, in labs, you can do that, but it requires a lot of like, particle accelerators and stuff. And it's not really worth anything. Like it takes more money to do that than you would get from anything made out.
Okay.
Exactly. Or nuclear reactions like Brandon said. So the process of it just takes a lot of time and a lot of money and a lot of energy. So not really efficient. But back in the day, the alchemy was like, someone was trying to figure out like, is there a way to just like convert iron to gold, like using different, they were just mixing stuff together and trying to do it, but no one ever did it. So yeah, it's a good question. Okay, anything else? All right, then I will break you out to breakout rooms. We only have one homework assignment that's due today, but you can get started on the regular homework, which is due on Sunday. So I will see you guys next Wednesday, because Monday is Memorial Day. We do not have class. And then Wednesday we will go over chapter 3. And then I might post a little YouTube video going over like review for exam 1, because our exam 1 will be the week after that. So I'll definitely do that. And then, so today we're doing the basic homework. So I will split you into 6 breakout rooms, 4 to 5 people per breakout room. And I'll go around slowly and just ask if you have any questions, or actually, how's this? If you have any questions, you can back out of the breakout room and ask me. I'll just stay in the lobby because I'm not sure who has questions at every time. So yeah, okay. Thank you for listening to me. I'm gonna cancel the recording now. Where's the recording? So pause, stop recording. All right.